Hello, my name is Taras and I would like to present you our recent work about using novel matrix multiplication architecture for neural network implementation. As we all know that the matrix operations are essential operations in all types of computer algorithms, including machine learning, including signal processing, computer vision. Everything can be described in a matrix. For example, here you have a good old feed-forward multi-layer perceptron and a set of matrix equations to calculate the state of every layer by just multiplying an input vector times weights matrix and applying a transfer function, some kind of sigmoid. All kind of fully connected networks like restricted Boltzmann machines, deep belief networks, autoencoders, they normally require multiplication of direct and transpose matrices, as you have to recreate the state of your input level, taking the vector of outputs and multiplying by a transpose matrix of weights. Also, learning algorithms, gradient descent, all kinds of backpropagation and contrastive divergence, they all have efficient matrix versions. Actually, this is a traditional way to train the network. Also, neural matrix computations have some interesting properties. First is the locality of the computations. Normally, when we are computing the state of one layer, we are immediately reusing the result to compute the state of the next layer. We don't have to store lots of intermediate results. So it reduces the amount of memory that we need. Also, the limited data range. We all work normally with the preprocessed data with normalized input, and also the transfer function itself is a hard limiter between -1 and 1 or between 0 and 1. So the limited data range is very good for a fixed point. We can avoid hardware costly floating point implementation. Also, we can reuse the same hardware blocks for network implementation for the computation of the state of the network, as well as for training, as mathematics is mostly the same. What about spiking neural networks that is mostly interesting for all of us? Well, if you modify your transfer functions, that it will be function not only from input and your weight matrix, but also add a time variable. So if you can modify the membrane degradation potential, then you can calculate the certain types of spiking neural network as well. So matrix computations and neural networks are big friends. How can we accelerate it in hardware? We are using FPGAs. FPGA chips are the wonderful technology. Actually, these are the chips that can emulate virtually any logical function. More than FPGAs, they also include numerous and very, very potent arithmetic cores, as well as a fast distributed memory. So they provide a sheer power for massive parallel computations, while and staying really, really energy efficient and fully reconfigurable, which is important. Of course, the architecture is too complicated to describe in 5 minutes, so I just emphasize what does it can. In the center of that neural processor lies the matrix processor that can perform virtually any combination of matrix by matrix, matrix by vector, matrix by transpose vector, multiplication, addition, dot product in O(n) squared time, with matrices up to 1000 on a single chip. Just for information, an MNIST solver, if we take autoencoder or restricted Boltzmann machine, it will take 784 neurons by 300 or 500 at most. So to recognize the text, we will not even use a single chip. The current processing speed estimated is on 300 giga operations per second on a 16-bit fixed point data. To my knowledge, this is the fastest single chip implementation till the day. With the possibility of computing straight and transpose matrices. Another interesting property is that our core has a very nice locality of the connections. We don't have long and wide data lines, and every hardware designer knows that such lines limit strictly your timing parameters, and your energy consumption suddenly grows. And if you try to implement an ASIC, you need 2 additional layers of metallization, so the cost is rising and the productivity is falling. We have implemented interesting version of architecture called systolic array, and it seems that it does the job. Another thing is that despite we are processing the full network layer in parallel, we need only single transfer sigmoid function for the whole core. So actually I can implement virtually all kinds of transfer functions and changing on the flyness, I can do a memory mapped function. And the full core is seamlessly integrated in systems on chip using standard AMBA or Avalon buses. So I can create an IP core, and you can reuse it in the technology you want. You can connect it to your processor or bigger system. I will be glad to answer all your questions and give you more information near my poster. Thank you for your attention.